This featured presentation will take you through the strange and weird matters of existence, wormholes, black holes, and unexplained phenomena. Wormholes vanish just as quickly as they form. Schwarzschild wormholes are vacuums that bridge a black hole and a white hole together. This wormhole, however, is unstable. If it were to be held open, though, the wormhole would be closed, according to Schwarzschild's calculations. Wormholes have at least two mouths that are connected through a path, or a mouth. If the wormhole is traversable, matter can travel through it from one mouth or opening to the other, and a human would be able to pass through it. Intra-universe wormholes connect point A in a universe to point B, or even connect two universes together. They connect 2 points in space-time, a fourth dimension, thus creating a possibility of time travel. A human can only go through an event horizon in one direction, but both ends of the hole has that event horizon, thus leaving the human trapped in the middle of the wormhole. Bear in mind, however, that wormholes do not provide faster than light speed travel and are only a shortcut. Cosmic strings are the product of symmetry breaking. In the early universe, extremely high temperatures will cause the universe to pass through a succession of phase transitions, one of them being cosmic strings. Cosmic strings appear in the form of carrying energy. They serve as a structure that attracts their neighboring matter. When strings evolve larger, they seed into matter energy density of the universe. No doubt that the universe is filled with strange things, from terrestrial planets to comets to planets and dwarfs. What is in between all that mess? Matter, hydrogen, nothing? According to Albert Einstein's theories of relativity, he states that gravity is the force that does the bending. Imagine this. Shine the beam of a bright flashlight so that the light flashes past the edge of the sun and into space. Now imagine standing on the other side of the sun. In that perspective, the light will appear bent towards the sun like a dimple in space. Now imagine this. If you shine the flashlight near the edge of a black hole, light cannot even escape. The other side, however, will only see a huge light beam. Is space like nothingness now? Weird nothingness always appears to be something. Black holes are sitting everywhere in the universe, including our own Milky Way. The mystery behind this black hole is that the swirling and devouring it does causes a lot of friction and thus should generate enormous energy emitting off bright light. Instead, it's faint. Very, very faint. Researchers of the Gemini Observatory question why. Is there not much stuff falling in, or is it falling directly in instead of swirling, or some unknown effect preventing the radiation from being seen? The sun provides energy to us from harsh droughts to sunny days on the beach. This is because it's so hot. The closer you get to a sun's core, the more hotter it should be, just like how if you get closer to fire, it's hottest at the center, at the core. One exception, the sun. The sun's temperature rises sharply in the sun's atmosphere and gets cooler towards the middle. There's a law that says this shouldn't be so. The second law of thermodynamics states that the temperature can only drop when you move away from a heat source, but the sun is apparently defying that law.
In general, a black hole is a part of space that is made up of so much mass that its gravitational pull is greater than that of the sun. In fact, its pull is so strong that anything within its reach is doomed to never escape, not even light. A black hole forms when massive stars explode into a supernova. A star explodes when the hydrogen within the star runs out and there is nothing left to balance with the gravitational pull of the star. The gravity pulls the star towards its center, creating a black hole. But not just any star can collapse and become a black hole. Only a massive star that holds more than 3 times the mass of the sun can become a black hole. Any star smaller than this will become a white dwarf or a neutron star. The size and weight of a black hole is usually compared to that of the sun. A stellar black hole, for example, is expected to have the mass of approximately 10 times the mass of the sun. Its weight would be around 1 million times that of the sun. Why do black holes suck so much? Since large mass comes with strong gravity, after a massive star dies out, the gravity of the star stays with the newly formed black hole. Later on, 5 times the mass of the sun is locked into a 30-kilometer diameter sphere. Because the gravity would be so great at this point, this is what makes the black hole suck in everything that comes near it. Oh, massive objects like black holes tend to alter time and space, so basic geometry rules don't apply. Therefore, a black hole possesses some unusual characteristics. For instance, it has a boundary called an event horizon, which is a spherical surface that marks the reach of a black hole. That means that anything that comes within the event horizon will be caught in the black hole forever. No light, radio waves, or radiation can escape a black hole's pull, and so this makes it difficult to detect the existence of one. It's only possible to detect a black hole when it's close to another star. Once this is true, one way to do it is by using X-rays. First of all, black holes pull surrounding gases towards its center, and this gas is spun and heated. This hot gas sends out X-rays, so astronomers use this to find any black holes. A quasar, which is short for quasi-stellar radio source, or QSR, is known to be the brightest and farthest object in space. Though often mistaken as stars because of their bright light, quasars are actually the heart of distant galaxies. But there are ways to figure out the difference between a quasar and a star. Further studies show that the lines of their spectra contain things known as red shifts. These red shifts indicate that the quasars are moving away from the Milky Way at speeds up to 95% of the speed of light. Quasars send out radio waves, X-rays, infrared, and light. Some have visible jets. Each one has a slanted dust ring which manifests the radiation that comes from the accretion disk. Although small in size compared to the other objects in space, quasars contain tremendous amounts of energy. The very first pulsar was discovered in 1967, but since then, thousands more have been found. Most are found in the Milky Way galaxy, but some others were spotted in globular clusters. Pulsars are rotating neutron stars that are immensely magnetic. While it's spinning, a pulsar sends out a radio beam that comes from each of its magnetic poles. Eventually, the pulsar uses up its energy and spins slower as this happens. In several million years, the spinning neutron star will spin too slowly to send out any radio waves and it will vanish. To find pulsars, astronomers use the radio waves that the pulsars send out. Each time a radio wave passes by Earth, astronomers detect its pulse and conclude on the possible existence of a pulsar. Various pulsars that have been found have been classified with names such as crab pulsars, binary pulsars, optical pulsars, and Vela pulsars.